Good evening, everybody. I'm Michelle Doherty, head of the physics department, and I'm so pleased to have you here with us to help us celebrate Morgan's promotion to professor. After doing his undergraduate degree at the University of Chicago, Morgan obtained his PhD degree from the University of California, Riverside in 2001. And we were very fortunate when he decided to move to Imperial to our high energy physics group in April 2006. He was awarded an STFC Advanced Fellowship a couple of years later, and then 3 years after that, he became a lecturer in the department, so from October 2011. Now, Morgan is an internationally recognized leader in the global field of neutrino physics, and we're really very proud of his high-profile research. But not only that, he is a passionate science communicator, and he enthuses his students with his love of physics. And he's also a strong advocate for diversity and inclusivity. And in fact, he chairs our own departmental Juno committee. Before I give the floor to Morgan, though, a few housekeeping ideas for you. Now, if we were able to do this in person, I would be telling you all what to do if a fire alarm went off. But of course, on this occasion, I don't need to tell you that. What I do want to tell you, though, is that if you want to submit questions at any point, please use the Q&A on the side of the screen. Keep in mind the event is being recorded, so if you do not wish your name to be read out with your question, then please submit the question anonymously. If you like a question someone else has asked on the Q&A, then you can give it a thumbs up, and we will make sure that we ask the most popular questions first. And then, without further ado, it gives me great pleasure to hand over to Professor Morgan Wascko to tell us about searching for new physics with ghost particles. Morgan, the floor is yours.
Well, thank you very much, Michelle, for that really nice introduction. And thank you to everybody who's joined. I'm sorry we're not doing this in person, but what I thought is that we could pretend that we are. So suppose you dropped by my office and you asked me about my research. What would happen? I'd talk about it, probably a lot more than you. I'd write on the whiteboard, and I'd show you some photos of things that my teams have built. So let's just do that for the next little while. We'll start with some background for the topic, and also all of my research career happens in the context of the Standard Model of Particle Physics, which describes the elementary constituents of matter and their interactions. This chart shows all the matter particles. The quarks are in purple, the green are the leptons, and then these are the force carrier mediator particles and the Higgs boson, which gives mass to the leptons. Now, down here, these are the neutrinos. This is the subject of my research and this talk. And I want to point out here that neutrinos are paired with a charged lepton counterpart. So a nu e is paired with an electron, a nu mu is paired with a muon, a nu tau with a tau particle. There are 3 generations of matter, and each generation is heavier than the previous one. The muon here is 200 times heavier than the electron. And these are the 4 particles I'm going to talk about most in this talk: electron and electron neutrino, muon, muon neutrino, and of course, their antimatter counterparts. Each particle has an antimatter counterpart. For the neutrino, it's an antineutrino, and we represent that with a little bar on top of the nu symbol. Okay, so the next thing I want to talk about is symmetries in nature. Particle physics uses symmetries to study the subatomic universe. And symmetries appear when objects or events are identical when transformed in some specific way. So as an intuitive example, I want to talk about rotational symmetry. So that you can see there's a picture here of a 4-leaf clover, and if you rotated that 4-leaf clover by 90 degrees, it would appear to be the same, and you could rotate another 90 degrees and it would be the same. So there's a rotational symmetry there. And this pattern below has a more complex, maybe more interesting rotational symmetry. But rotational symmetry can actually be more interesting with more dimensions. And I want to do a little demonstration, which you can join if you like, if you have a piece of paper or a card near to hand. For me, the thing that's near to hand is this 1981 Walter Payton NFL card. So I'll take Walter Payton and rotate him about the horizontal axis, and now about the vertical axis. And what you notice is that sweetness is upside down here, which is equivalent to a rotation in the third dimension. So what I wanted to show here is that even a simple thing like rotational symmetry becomes more interesting and rich when we add dimensions to it. So now I'll put sweetness, give him a little Super Bowl shuffle back into his protective case. The reason that we love symmetries in particle physics is because of the work of Emmy Noether, who's shown here. She discovered and proved a theorem that says for any symmetry of a physical system, there's a corresponding conserved quantity. So the rotational symmetry that I was just talking about leads to the conservation of angular momentum. And in the context of physics, what I mean is of these measurements, I mean that rotational symmetry says that if I look over here, the laws of physics are the same as they are if I look over here. I can rotate any frame and things are operating the same in either direction. And that implies that the quantity angular momentum is conserved. And vice versa, if you discover a conserved quantity, there is probably a symmetry that is related to that. So the big picture that I'm going to frame my neutrino oscillation research in is related to the conservation of the matter-antimatter balance. It's related to what we call CP symmetry. So CP stands for charge and parity. Charge conjugation is the act of transforming matter particles into antimatter particles. And a parity transformation is inverting all of the coordinates. So it's basically looking at the world upside down and in a mirror. And if we want to test CP symmetry for particles, we're asking questions like, are the laws of physics the same for a left-handed electron and a right-handed positron? So handedness is related to parity. Consider your left hand, another little demonstration you can join if you like. Imagine that an electron is spinning in the direction of your fingers here, and it's moving in the direction of your thumb. Your right hand has the fingers indicating a spin in the other direction relative to the motion of the electrons or positrons. And the reason that left-handed and right-handed things are different is you notice that I've got the thumbs oriented in the same direction here, but the fingers are spinning in the opposite directions. But if I make the fingers spin in the same directions, now the thumbs are pointed in the opposite ways. So handedness is related to parity transformations, and it's an important part of it, and it's an important part of the standard model. The question for neutrinos that I want to talk about is, does muon to electron neutrino oscillation differ from muon to electron antineutrino oscillation? Now, particle physics likes to ask big questions, and we want to say things like, how did we get here? But more technical questions are better suited to actually successfully answering them in a quantitative way. So we would ask a question more like, what's the mechanism by which the universe transformed from a matter-antimatter symmetric state at the Big Bang to what we see today? Or in a more pithy way, where's all the antimatter? Neutrino oscillation, which I'll talk about for most of this talk, offers us a new test of CP symmetry. Now, the matter-antimatter asymmetry is also called a baryon asymmetry because baryons are the name we give to heavy particles that are constituents of quarks. And in order for a baryon asymmetry to develop, Andrei Sakharov wrote down in 1967 that several conditions need to be true, one of which is that there needs to be some difference between matter and antimatter. And that difference is CP violation. We know that CP is violated by some quark decays, but that level of CP violation is not large enough to explain how the universe developed into all matter, or at least matter-dominated universe. But CP violation by neutrinos may be much larger, and if it is, that could be the CP violation that's needed to explain the baryon asymmetry. So the idea that we have in neutrino physics is, let's find out. So let's get right into it with neutrinos and talk about this ghost particle aspect. we express the probability of particle interactions in terms of cross-sections. A cross-section is a numerical number. It comes in with units of area, and you can think of it as being related to the size of a bullseye on a target. So an interaction with a small cross-section has a small bullseye, and a large cross-section has a large bullseye. Look at these two examples here. On the left, there are neutrinos being thrown at a proton target. That has a very small cross-section, so the bullseye is small. Whereas if you throw protons at a proton target, it's got a bigger bullseye because the cross-section is 10 to the 11th times bigger. It's 100 billion times more likely that a proton will interact with another proton than that a neutrino would interact with a proton. So that's why we call them ghost particles. That small cross-section means that we have to create many chances for an interaction to occur if we actually want to see things happening. We need an intense beam, we need a large detector, and we need patience. We need to let this run for a long time to collect enough events that we can learn something about the universe. And as I was saying before, the neutrino is paired with a charged lepton partner. So the main particle that's produced by an interaction of a neutrino identifies the neutrino's flavor. So if we see an electron appear in our detector, then we know that we had an electron neutrino that created that. Interestingly, if neutrinos have mass, then a neutrino that's produced as a nu mu might be observed as a nu e after traveling a distance L. And when I say produced as a nu mu, I mean that right at the point where it was created in conjunction with a charged muon. And when I say it interacts as a nu e, an electron is produced in the detector. This phenomenon is called neutrino oscillation. Neutrino oscillation comes about because of the interference of the flavor and masses of neutrinos. So for a simple example, so that I can draw a nice, easy picture, in a world with two neutrinos, if the weak flavor eigenstates are mu and e, and if they're different from the mass eigenstates 1 and 2, then we can write those weak states as a mixture of the mass states. Now, let me just say a little jargon explanation. Eigenstate is a term borrowed from German. It means the characteristic state. And basically, it just means the characteristics that the neutrino wave function has. And we see those characteristics when the particles interact. So if the basis vectors of the mass 1 and 2 are rotated by an angle theta around nu e and nu mu, then we can write those weak states as a mixture of mass states. Pictorially, we imagine that a muon neutrino exists right here, just purely on the nu mu axis. But because of this rotation, there's a little bit of nu 2 and a little bit of nu 1 mixed up in that muon neutrino state. So as that muon neutrino propagates through space, because of its mixture with nu 1 and nu 2, now it has a probability of appearing later as a nu e. And we can use the rules of quantum mechanics to calculate the probability of that happening, and it's given by this formula, which I will talk about more on this slide. In the formula, there are two fundamental parameters. One is theta 1, 2, that's the magnitude of oscillation. When it's written as sine squared 2 theta 1, 2, that's the magnitude of the oscillation. It's related to the rotation angle between those basis vectors. And this term here, delta m squared, is related to the period of the oscillation. How far does a neutrino travel as it's going from one flavor into another? There are two experimental parameters in the formula, L, the distance traveled, and E, which is the neutrino energy. So this sine squared times 1.27 delta m squared L over E, this is the oscillatory parts of the neutrino oscillation formula. And neutrinos can both disappear and appear. So if we want to build some experiments to explore this disappearance and appearance, we would consider the places where we want to do it. We want to create a muon neutrino beam and right away make a measurement. So very close to where the neutrinos are created, we're going to measure the number of neutrinos and compare it to our expectation. The observation here is in blue and the expectation is in black. And if we make a ratio of the observed to the expected number of neutrinos, we get something that's roughly flat. along here as a function of neutrino energy. Now, suppose we move our detector or build another one some distance L away from where the neutrinos are created. Now we have a situation like this. This black curve shows our expectation, which we tuned with our observations at the near site. And we observe this blue curve where there's a deficit of events compared to the expectation. And if we look at the ratio of the expected or the observed to the expected, we're going to see this beautiful dip right here, showing that muon neutrinos are indeed disappearing. Now, suppose we want to check if they're appearing in the electron mode. We build a detector that can see electrons. And again, we are looking for something above our expectation, above some background that may be there. And then if we look at the ratio, we're going to see something well above 1 if things are appearing. And that's a neutrino oscillation experiment in a nutshell. The essence of the measurement is getting at neutrino flavor and neutrino energy. So we need to create beams of neutrinos. We need a detector that can distinguish muon neutrinos from electron neutrinos, and we want to measure their energies. And also, we need a large detector that can do all these things. But luckily, there is such a detector. It's called Super Kamiokande, and it's in Japan. Now, if you'll pardon my very silly pun, this really is a super neutrino detector. First of all, it's huge. There's a gigantic amount of ultra-pure water, 50 kilotons, 50,000 tons of water. If you work out the number of molecules in there, that's about 3 times 10 to the 31 molecules. My children would be very excited to tell you that that number has a name. You don't just have to write it in boring scientific notation. The name is 30 nonillion molecules. Around this huge amount of water are 11,000 20-inch photomultiplier tubes in the inner detector. That's this part here labeled ID. And then there's an outer detector shell around there with another 2,000 photomultiplier tubes. These are highly sensitive light detectors. It's basically the opposite of a light bulb. In a light bulb, you put an electric current in and you shoot light out. This device, when light hits it, a little signal comes out, an electric signal comes out. You can detect that, read it out, and it tells you how many photons hit the PMT and when they hit. So you can use that quantitative information and precise timing to learn about what's happening inside your detector. So in Super K, the PMTs detect Cherenkov radiation, which is produced by high energy particles created when the neutrinos interact with the water molecules, all 30 nonillion of them. Now, what's Cherenkov radiation, you ask? Good question. Cherenkov radiation is similar to a sonic boom, but it happens with light. If a charged particle traverses a dielectric medium like water or glass, it can actually exceed the speed of light in that medium. Now, I didn't say something controversial there. When light goes through water or glass, its velocity is reduced by a factor of the index of refraction. So light is traveling slower than its speed in a vacuum while it goes through this medium. But the charged particle can go through very close to the speed of light. And that's like exceeding the speed of sound for an airplane. And what happens is that light is created in a little shock wave, kind of like this little wake from the duck swimming through the water. And the photons come out in a cone. So those photons are Cherenkov radiation. And Super K is designed to be able to detect that radiation when the Cherenkov light reaches the wall and those photomultiplier tubes. Here's what it looks like when that happens. In these event displays from Super Kamiokande, each of the gray squares here represents one of the PMTs. The gray ones saw no light. The colored squares represent PMTs that did see light. The size of the colored square is related to how much light was observed, and the color is related to the time. So bigger is more light, smaller is less light. And in these pictures, blue is a little earlier and red is a little later. So in this muon ring, we see the particle is coming down at a little bit of an angle, and so the light is hitting the top of that ring before it hits the bottom of the ring, and so you get the difference in the color. You also may notice that the outside edge of the muon ring is very sharp, but the edge of the electron ring is really kind of fuzzy. And that happens because of the difference in the mass between the muon and the electron. The electron is 200 times lighter than the muon, so it kind of gets bounced around by the electric fields of the molecules in the water. At the atomic level, this is happening. Whereas the muon is 200 times heavier, it just barrels through, and its path is deflected much less, so it makes a nice clean ring. And we can use that to separate muons from electrons with high precision. Now we can take that super K detector and it's actually been used. It's been running for over 25 years, and very precise measurements from naturally occurring neutrinos have been made of solar neutrinos coming from the sun, atmospheric neutrinos coming from cosmic rays interacting in the Earth's atmosphere. It can also be used in conjunction with an accelerator-based neutrino beam, and that's what this diagram describes. The idea here is to take an accelerator to create an energetic beam of protons and impinge it on a light target, focus all the meson particles. Mesons are lighter particles than baryons, but they're still made of quarks. You focus them into a decay volume where they travel along and decay into lighter things, which includes neutrinos. At the end of the decay volume, there's a huge beam stop. It stops all the charged particles, but the neutrinos, because they're ghost particles, just mostly tend to pass through. And then we can put some detectors in the way, a near detector to measure the neutrinos before they oscillate, and a far detector to look for the oscillation. And I'd also like to mention that we can do a lot of work to really enhance the strength and the quality of the neutrino beam by using magnetic focusing horns. So this is a diagram from the T2K experiment, which I'll explain in a few slides, of the 3 magnetic horns that focus and sign select the particles, so we can create neutrino beams for that experiment. Now, as I said, the essence of the measurement is the lepton flavor and the energy. Now, the neutrino's energy is converted into the masses and the energies of all the secondary particles. So if we're able to measure secondary particles, we can maybe improve our energy reconstruction, get a little bit closer to the true neutrino energy that interacted in our detector. Now, remember, I said that to produce Cherenkov radiation, a particle needs to be traveling faster than the speed of light in the water. Many particles are not traveling faster than that. These little secondary particles, which I've represented by little short lines here, they may not be producing Cherenkov light, so they would be invisible to the super K detector. In some ways, that's an advantage because you can just look for the leading lepton, and that's very important for a sort of first generation neutrino oscillation experiment. But when you want to get a little bit more precise, it's nice to be able to look at these extra particles. So you want a detector that can observe lower energy secondaries. And the Cyboon experiment that I worked on at Fermilab is an example of a detector that can do that. So before I talk about Cyboon, I want to explain another phenomenon called scintillation. Now, scintillation happens if this charged particle, a muon say, is going through our detector medium. It can bump an atomic electron and raise it into a higher energy orbital. Then it passes out of the picture. Later, the electron comes back down to a lower energy state and releases that energy in the form of light. That light is scintillation light. Many materials produce scintillation light, and you can dope plastics with scintillators and mold them or form them into all kinds of creative shapes. And there's lots of particle detectors that use this technology, including the Cyboon experiment. So here's a slide that I pulled directly from a talk that I gave 10 years ago on some Cyboon results. Cyboon was a scintillator detector that was placed in the booster neutrino beam. It was in a near position relative to the mini boon detector. And so I'll talk about all these things a little bit in the next few slides. The heart of Cyboon was Cy-bar, the scintillating bar neutrino vertex detector. So you can see in this photograph here, Cy-bar was a series of horizontal and vertical scintillator strips with wavelength shifting fibers, that's these little green fibers, running down the center of each one. And the idea is that charged particles pass through the detector materials and create scintillation light within each strip. It's picked up by the wavelength shifting fiber and read out by an individual photomultiplier tube. You can then track each particle as it goes through the detector because it's only leaving a trace within that small scintillator strip, and that's why we call it a fine-grained detector. SIBUN also had another detector downstream called the muon range detector. This was also scintillator, but it had sheets of thick iron in between the scintillator planes, and that slows down energetic muons and allows us to make them stop, and we use that to infer their energy. Now, both the SIBAR and MRD detectors were assembled in different sites at Fermilab and then driven over to the SIBUN detector hall and lowered with a gigantic crane in about 2007. Here are some event displays of SIBUN data events. On the left is a neutrino interaction, and on the right is an antineutrino interaction. And in these displays, the green box is SIBAR. The MRD is shown by these sort of light brown boxes here. And each little red dot is a scintillator strip that observed a light signal. And again, the size of the dot is proportional to the amount of light that was observed. Now you can see here in this neutrino interaction, what we are observing is a nu interacting with a neutron in the detector material, producing a mu minus and a proton. So the mu minus makes this long, thin track and goes into the muon range detector and stops. The proton is a short little stubby track that would have been invisible in a Cherenkov detector. In the antineutrino event, the antineutrino interacts on a proton and produces a mu plus and a neutron. So this mu plus looks very similar to the mu minus in SIBAR and in the MRD, but the neutron is actually invisible initially. So here's a blow up of the vertex area, and you see there's nothing coming off of the neutrino interaction vertex here. It's because the neutron is a neutral particle. It produces no scintillation light, but it can interact through the strong force with the free protons in the plastic of the detector material, and then give them a big blob of energy. And so that's what these little splats are here from a neutron bumping protons farther away from the vertex. So we can actually do a decent job of separating these neutrino from antineutrino events, but it would be nice to make it a little bit more precise. And I'll come on to how we can do that in a few slides. SIBUN made what were then world-leading measurements of muon neutrino and muon antineutrino disappearance jointly with the mini-moon experiment. And here are some of the result plots from that. We also made precise neutrino and antineutrino cross-section measurements. Now, I haven't talked yet about neutral pions or the neutral current interaction, but this is an important channel for doing an electron-neutrino appearance. This is a kaon constraints that SIBUN made, and that's also important for the NUI appearance channels. Just trust me that they're both very cool, and we use them as input to the T2K measurements. So that brings us on to T2K, which is the Tokai to Kamioka experiment. So we, not surprisingly, start in Tokai, where we have a neutrino beam that's created with the proton accelerator at the J-Park facility. That neutrino beam is directed towards Super K, but is first sampled with near detectors also on the J-Park site. Before the neutrinos travel 295 kilometers across Honshu to Kamioka, where they're observed by Super K, which we've been talking about. Here's a couple of nice photos of T2K. Here's the accelerator complex at J-Park, culminating in the 30 GeV proton ring, which sends the creates 30 GeV protons, which are sent into the neutrino beam. And this is one of the focusing horns for the T2K neutrino beam. 280 meters after the neutrino target, we have the ND280 detector, which is a series of finely segmented detectors in a magnetic field. And the magnetic field is the key to the matter-antimatter separation, and I'll talk about that in a little bit. But first, let's look at some T2K neutrino mode data. So remember the cartoons I showed you earlier. This is what we were expecting for new mu disappearance. We have this expected curve and this little observation with a dip, and that is indeed what we see in T2K data, which is shown here. This black curve shows the unoscillated expected spectrum, and then the black points show our data. And so you can see in the ratio, there's this beautiful dip showing the oscillation. And in the electron neutrino appearance signal here, we have a fairly big signal this curve actually shows the best fit to the oscillated hypothesis, but you can see the size of the appearances compared to the expected background down here in the ratio, where you can see that these bins are well above a ratio of 1. So we are seeing a sizable electron-neutrino appearance in the data. For that observation, Ko Nishikawa, our founding spokesperson, and all TDK members were awarded the the Breakthrough Prize for Fundamental Physics in 2016. And I wanted to show you my Breakthrough Prize medal, which has pride of place here in my office, right next to Walter Payton. Now, back onto the matter-antimatter question. As I mentioned when I was talking about the neutrino beams, we actually can use magnetic fields to bend charged particles. Charged particle tracks bend when they pass through magnetic fields. And note, particles have opposite charges from their antiparticles. So a particle and its antiparticle curve in different directions. So if we have a magnetized detector, then we can tell a muon neutrino, which has a curve in this direction, say, from a muon antineutrino, because the curve of the muon goes in the other direction. So we want a detector with a magnetic field to separate the matter from antimatter, and ND280 indeed has that. And using ND280, we have made very precise measurements of antineutrino data. So these plots look very similar to what I showed you for neutrino mode, but this is actually completely different. This is antineutrino data. It's a different data set. But again, the black curve shows the expected unoscillated pattern, and then we see a dip in the disappearance of the antineutrinos compared to our expectation. And then this plot on the right shows the electron antineutrino appearance, where again many of our bins are above the ratio to the unoscillated of 1. Now, science progresses by using yesterday's discovery as a tool for our new discoveries. So we're now using this electron neutrino and antineutrino appearance as a tool to search for CP violation. And CP violation would appear in T2K as a modification of the neutrino and antineutrino oscillation probabilities. So this graph here shows the number of antineutrino events versus the number of neutrino events. And there are several cases here because there are actually 3 neutrino flavors, and the full phenomenology of neutrino oscillations is more complex than I've discussed here today, but that's only because I want to actually finish on time. This gray circle shows roughly what we would expect with no CP violation, but with neutrino oscillation. If we have maximal CP violation, we could have a mode where the neutrino appearance is enhanced and the antineutrino appearance is suppressed. Or we could have a mode where the neutrino appearance is suppressed and antineutrino enhanced. So this is those cases, and this is where the T-decay data lie. So we're actually seeing something that seems to indicate the enhancement of neutrinos and suppression of antineutrinos. It's consistent with maximal CP violation, and we're able to show that at a fairly high statistical significance of 3 sigma. For this result, we published our results in the journal Nature, and actually got it on the cover of the journal. So it was very satisfying to have our really fun result given such a good place in the scientific community. And if you notice the date here, it was April 2020. So it was very nice to have some good news during the first lockdown. But let's try to stay upbeat, and we'll think about how do we take this 3 sigma observation from T2K and really explore it and make it high significance. For the future, we need even more precise detectors. Now, charged particles lose energy when they bump into atoms and molecules of the material that they're passing through. Denser material means more energy loss in a shorter distance. And a less dense material means longer particle tracks for the same energy. And that allows a finer resolution using the same detection methods. So what would be great is a gas-based fine-grained detector. And we've been working on one of those. First, I want to tell you about ionization. This is a stronger version, if you like, of scintillation. What happens in ionization is that a charged particle bumps an atomic electron with enough energy that it completely liberates it from the atom entirely. So it just shoots this electron all the way, very far away from the nucleus with which it was bound. The remaining atom is called an ion, and that charged ion and the electron can now be manipulated by electric and magnetic fields. So you put an electric field pointed here, the ions will drift this way, and the electrons will drift the other way, and the electrons, being much smaller, drift much faster. So we can use that to make a particle detector. So if we apply an electric field across a volume of gas, we can build a particle detector using this method. And so when a charged particle passes through the volume, it ionizes the gas along the trajectory. And then the electric field drifts the charge, the electrons and the ions in opposite directions. And those liberated electrons impact sensors on the wall of the gas volume, and then they can be measured. Those electrons can be measured, and then the information about the track that went through can be reconstructed from that information. So we built a prototype of a detector like that, and so here's a few photos of that. These copper rings that you see here form the field cage that creates the electric field that drifts the electrons and ions apart. You can see members of the team assembling the sensor wall, which is made of electrostatic meshes back in here. And now in this photo, the electrostatic meshes are in place, and you can see the copper rings of the field cage all inside of a big, thick steel pressure vessel. And here's a picture of the pressure vessel behind me, and you can guess here what my favorite movie is. This is the pressure vessel containing our TPC detector. It's holding 5 atmospheres of gas inside, so it is a very high pressure device. And we took that to a charged particle test beam at CERN and sent charged particles through it to characterize and test the performance. And now we're working to refine and improve this technology and everything we learned from that experience, and apply it to the next generation of neutrino experiments. So now moving on to the next generation of experiments, there are going to be 2 long baseline accelerator-based neutrino experiments, one in Japan called Hyperkamiokande, one in the United States called DUNE. Now Hyperkamiokande, shown here on the right, is a water shrink-off detector. It's 8 times larger than Superkamiokande, so it's a well-known, well-understood technology, but even bigger than an already big detector. It will be located very close to Super K, so its baseline is still 295 kilometers, and it will be fed with an upgraded, meaning more powerful J-Park neutrino beam, the one that is feeding neutrinos and antineutrinos to TDK now. In the US, we're working on building an experiment called the Deep Underground Neutrino Experiment, DUNE. DUNE is actually comprised of liquid argon TPC detectors. So I'll say a few more words about liquid argon on the next slide. And we'll build a high pressure gas argon TPC in the near detector. There will be a 1,300 kilometer baseline across the USA. So this neutrino beam will go from Fermilab just outside of Chicago, where SciBoom was located, 1,300 kilometers across the US to western South Dakota at the SURF facility. And it will be fed by a new neutrino beam that's being built at Fermilab right now. So DUNE the FAR detectors will be comprised of 4 separate modules, each 17 kilotons, so 17,000 tons of argon, which is cooled to minus 184 degrees Celsius. Now, for those of you watching from America, that's about minus 300 Fahrenheit. It's really cold. But at that temperature, the gas argon becomes a liquid, and so it's very dense, but you can still make a TPC out of it. Charged particles will ionize the argon molecule, or the argon atoms, and then you can drift the electrons away and sense them at the walls of the detector. The DUNE FAR detectors will be located 1.5 kilometers underground. So DUNE will be pretty interesting in terms of getting several kilotons of cryogenic material that far underground. It's a big and interesting challenge, and it's going to produce great physics results. So this plot here shows the sensitivity to CP violation. So this is the CP parameter, and these values here show the maximal CP violation scenarios that I pointed out on the TDK plot, where we saw neutrino and anti-neutrino and neutrino appearance signals. And I mentioned in passing that TDK has a 3 sigma statistically significant result. Dune has the capability to make 5 sigma or better, depending on the true value of the parameter that governs CP violation, which is called delta. So the unprecedented underground cryogenic detectors will yield unprecedented sensitivity to CP violation. So before finishing up, I just want to bring it back to the big picture question: how did all this develop? Where is all the antimatter? So to conclude, neutrino oscillation is the right way to search for that CP violation and answer the question, where is all the antimatter? It's one of the CP violation is one of the necessary conditions for the formation of a matter-dominated universe. And I hope I've given you a little bit of an idea of why I think neutrino detectors are complex and interesting tools in this quest. And with new and better neutrino detectors, the discovery of CP violation by neutrinos is within reach. So I'd like to finish with a word of thanks to many colleagues for all the things that were shown in this talk. And thank you for watching. And that's me done.
Morgan, thank you so much. That was fantastic. Not only describing early work and the work that you were involved in, but the future work as well. So you've set the scene beautifully for us, and there are lots of questions. So do you want to take a sip?
Yes, please.
Because we've all been sitting and watching in awe, and you've been talking, so I appreciate time to sip. So let me start with the first question from Ayup. That question is it theoretically or experimentally possible to test the equivalence principle for neutrinos?
Interesting question, and I would say theoretically it's possible. Meaning there's not an in principle thing that forbids doing this in the laws of physics, but practicalities mean we are never going to do this. The mass of neutrinos, I glanced over it, but the mass of neutrinos is about 100,000 times lighter, or even more light than electrons, and we've never really done a good job of, or rather, I shouldn't say not done a good job. It's exceedingly hard to do gravitational experiments with electrons, and so it's just not really feasible to do a gravitational experiment with a neutrino.
Okay. The next one is from Ryan. He says, will there ever be compelling evidence for sterile neutrinos?
Well, again, I don't know if you're going to like my answer. Will there ever be compelling evidence? Gosh, I don't know. There is some evidence, but it's kind of contradicted by other observations, and so I wouldn't call the evidence yet compelling. And it seems difficult to imagine a scenario where that's going to become compelling. There is an experiment at Fermilab called Microboon, which is working on doing that, and a future one called SBN, which will short baseline neutrinos, will explore that question. I should mention for people watching this who don't know what sterile neutrinos are, sterile neutrinos are neutrinos whose existence is only hinted at by extra neutrino oscillation activity. They aren't observed through the weak interactions with the other standard model particles, and so that's why we call them sterile. They don't seem to have the normal interactions, the regular interactions that a neutrino does, but they do. If they exist, they could appear through neutrino oscillation phenomena. A more cheeky statement about stereo neutrinos is that stereo neutrinos are an experimentalist's worst nightmare, because you can never actually rule out the existence of stereo neutrinos. It could just be that their coupling is a little bit smaller than the sensitivity. So that's kind of the opposite of the question. Will there be compelling evidence? I don't know. Will they ever be ruled out? No.
Okay, thank you very much. Next one is from Pranav. The question is, instead of the entire universe being dominated by one type of matter, what is the chance that regions are dominated by matter or antimatter instead?
So it's a good question. And it's an area of interest and research, and so far there's no evidence for it. So you would, wherever there are regions of matter dominated versus antimatter dominated, there should be at the boundaries telltale signatures of matter antimatter annihilations, and we don't see that. But more precise measurements are planned and will be made, and so maybe we'll see something like that. And I could mention out of interest, at least to me, that my thesis work was looking for antimatter in cosmic rays, and we didn't see any. We saw we set limits on the fraction of cosmic rays that could be made of antimatter.
Okay, thank you. Next question, and I was wanting to ask this myself anyway, so I'm glad that Tepe has asked it, and that is, what was the most exciting moment so far in all the experiments you have worked on?
Well, Tepe, thank you for the question. Probably you were there with me, but I actually think that the most exciting moment was that I've experienced was the first inkling of the T2K electron neutrino appearance. So we in 2011, I think most people will remember that there was a horrible earthquake just offshore in Japan. It caused huge devastation across northern Japan, and obviously halted our experiment for more than a year. So we did a very fast effort, a strong effort to analyze the data quickly, and which we had been saving to try to collect as much as possible before we stopped the run. And we saw a very small signal, but starting to be interesting signal of electron neutrino appearance. And for me, that was the first time that I saw, because we were also seeing the muon neutrinos disappearing. That was the first time that I had seen neutrinos in my own experiment actually oscillating, obviously oscillating in a compelling way. So that was very exciting for me, and that's the breakthrough that, or the result that led to the breakthrough prize. So obviously other people thought it was pretty good too.
Okay, thank you. Questions are coming in thick and fast, Morgan. There's one from Ellis, who asks, what new physics may be discovered by your research in neutrinos or ghost particles? And are there any possible applications of your research? And if so, what are they?
So the new there's always a chance of seeing a result that's completely unexpected. So the new physics that we kind of are hoping to find, because we already know what it would look like, is CP violation. Mm-hmm. There may be more complex signatures of neutrinos appearing or disappearing, which could indicate something like stereo neutrinos, or there are other interesting results in particle physics right now. From the LHCb collaboration at CERN has just released a result showing a 3 sigma deviation in what's called the RK ratio. So it's decays of B mesons and decay mesons, so B quarks into strange quarks basically. And when they involve muons or electrons, they come out at different rates, which appears to be a violation of what we call lepton universality. It's probably not a violation of lepton universality, but there's something else going on in there. And that something else may manifest itself in a neutrino experiment. And so that's one of the great things about Dune and Hyper-K is there'll be such large data sets that we can look for really kind of new and original things that could be connected to the other things that we're seeing in particle physics.
Thank you, Morgan. That actually leads rather nicely into the next question, and that is from Sam Short, who says or asks, what do the next generation neutrino oscillation experiments look like? What's better than a bigger Cherenkov detector and a high pressure TPC?
Hi, Sam. I showed a picture of Sam on one of my slides, by the way. The next generation, I, along with several colleagues here at Imperial, hope that would be not a pion decay in flight beam, but a muon, a stored muon neutrino beam. Maybe just new storm, not something called new storm, which is a let's say a less souped up version of an experiment called the neutrino factory. But the idea is you capture muons and let them decay in a controlled storage ring, and that should give you very precise and well-controlled nu E bar or nu mu bar nu E beams, and then you can do really interesting matter antimatter comparisons with high precision there. There's quite a lot of measurements that could be made with a really big gas TPC and new storm, and I would love to work on that someday.
Thank you. Okay, so a question that is often asked of people that run large experiments, and this is from Camille. If you had an unlimited budget, what experiment would you run?
Unlimited. Yeah, I mean, so okay, unlimited budget is one thing, but I think one still has to be constrained by technological limits. So I think with an unlimited budget, I would shoot a neutrino factory through the center of the Earth.
Okay, maybe it's time to move on to the next.
You know, do it, but maybe not the center of the Earth, but because you want to have a lot of very large detectors in the Antarctic ice, so something really gigantic, and shoot something down there.
Okay, thank you. I then have an anonymous question. Is it possible for the rest of the antimatter to be beyond the observable universe as it was formed at the time of the Big Bang? Or is it just simply too far away for us to detect it as antimatter?
So that's an interesting question because it gets at aspects of relativity that are really kind of non-intuitive. But it's in the text of the question, right? That it's possible for parts of the universe to be beyond physical, the possibility of physically observing them. They're outside of our light cone. So is it possible for the universe to be made of antimatter out there? Maybe. I don't actually know. I don't know of a reason why it couldn't be, but we wouldn't be able to know that. So there's a theoretical reason why you can't know if that's there. And that theoretical reason why you can't know that's there, I think, is true. So let's make it a more fun answer and say yes.
Okay. Another anonymous question. How are the neutrino beams controlled if they aren't charged and have such a small cross-section? How do we know what type they start out as?
So that's a good question, and it's a hard business, but it basically comes down to those magnetic focusing horns. And the thing about the neutrino beam is once the particles decay and form those neutrinos, the neutrinos are just off and running. So they just do whatever they're gonna do. So you have to direct the particles that are decaying into the neutrinos in the best way that you can. And they are short-lived particles, so it happens fast. Mm-hmm. And that's why we use, in several generations of accelerator experiments, we've used these neutrino horns that just focus the mesons and point them and kind of, the neutrinos basically go ballistic, meaning they're fired off and then they just go. The neutrino factory idea that I talked about before is a little bit different. You can control the particles that are going to decay into the neutrino beam, and so you can get it more tightly collimated and do a little bit better job of controlling that beam. Sorry, what was the second part? What's the second part of the question?
How do we know what type they start out as?
So then you just put a detector near the starting point, and test whether or not you measure the flavor, you measure the energy of the neutrinos before they've had a chance to oscillate. Now it can get pretty complicated, because remember that in the oscillation formula there's delta m squared L over E. For very different values of delta m squared, you could have oscillations appearing with a short baseline, if they exist. And so that's what Saiboon and Miniboon did, that we were looking at a short baseline oscillation. And in some of those cases, neutrinos could be disappearing at the near detector and already having reappeared at the far detector. So then you have to have in your analysis, you have to be able to allow that the two detectors to sort of exchange that job, if you like.
Mm-hmm. Okay. Another question is, CPT is a nice thing to assume, but what are the limits of CPT violation?
Well, it's not just a nice thing to assume. If we assume that CPT is not, so CPT is charge parity and time reversal symmetry. Quantum field theory is predicated on that being a symmetry that is satisfied in the universe. If it's not satisfied, so first of all, that would be awesome. I mean, that would be the coolest new physics that anybody ever thought of. But everything you know about quantum field theory has to be rewritten in that case. So although it's awesome, and I kind of hope that happens, I don't know what we would do and how we talk about particles and do calculations after that.
Mm-hmm.
So the limits of CPT violation, I guess, are you asking, could we simultaneously measure CP violation and time reversal symmetry violation and see that they don't match up to CPT? And actually, Tepe is a better person to answer that question.
I don't think he's going to have the opportunity to. I'll try on the chat though. The final question I had in the list I have here, and I'll go looking in the Q&A if we've got any more time, but what other aspects of neutrino physics do we need to better understand to get 5 sigma for CP violation? And this is coming from Ryan.
Hi, Ryan. Thanks for joining. Ryan is another one of my many colleagues that I thanked in the talk. I mean, we really, so the flux errors will be probably controlled well enough with the near detector. I didn't mention all of the really clever components that the Hyper-K and Dune near detectors will have, but they will sample neutrinos as a function of distance from the center going off axis from the beam, and that gives you lots of information about different neutrino energies, and that will also allow us to constrain neutrino interaction cross-section. So I skimmed over a whole field of research that when neutrinos interact with a proton or the nucleus, all kinds of different things can happen in those secondary particles, and we need to kind of understand all of them from a bottom-up way. And I would say that the interesting thing there is that it's about 10 or 15 years more work at least, and that's a good problem for someone like me to have.
Okay, Morgan, thank you very much. I'm going to draw the questions to a close now, and I'd like to introduce Peter Dornan to everyone to give the vote of thanks. Peter has always been a valued advisor and mentor to Morgan, and he was in fact head of the high energy physics group when Morgan first joined the department. And Peter was instrumental, along with Dave Walk, in actually persuading Morgan to join us. And so we have lots to thank Peter for. He also helped to grow the neutrino activity that Morgan has so effectively developed into a large part of that group. So Peter, let me hand over to you. Thank you.
Hello. It's really my great pleasure to offer this vote of thanks to Morgan. This inspiring inaugural, and also the beautiful way he's answered the questions. I thought they were great. As you will have appreciated from the talk, neutrinos are absolutely crucial and also often rather confusing part in our attempts to understand the nature of particles and forces. Just when we feel we're beginning to understand things, neutrinos come along and they tell us we still have a lot to learn. They have intrigued us and advanced our knowledge like nothing else, and today they continue to do so, as Morgan has so beautifully shown. We go back to 1930 when Pauli postulated the existence of the neutrino to explain beta decay. I have done a terrible thing, he said. I have postulated a particle that cannot be detected. Well, he wasn't quite right. What we have heard today is that although it is difficult, we know now that we can detect them, albeit only a very small fraction of those which pass through our detectors are detected. But this makes experiments challenging, but equally it makes them very rewarding, as again we've heard today. It was 26 years after Pauli that we first saw the direct observation by Reynolds and Cowan in 1956. But then, as we've heard, we learned how to build neutrino beams from accelerators. And this allowed a really expansive area of neutrino sort of investigation. The first unexpected discovery, and there have been quite a few in the neutrino area, was by Steinberger, Lederman, and Schwarz in 1962, when they discovered that there was not just one neutrino, as people had thought, but there were two neutrinos, as Morgan has said, an electron neutrino and a muon neutrino. And so when the tau lepton was discovered in 1975, it was assumed there must be a third neutrino, the tau neutrino, and this was verified in 1989 by the LEP collider. During the 70s and 80s, the Imperial group at college, the Heinz group, was heavily involved with experiments using neutrino beams. This was to investigate the structure of protons and neutrons. But as we moved into the 90s, the interest in this and neutrinos generally waned, and we stopped our neutrino activities. But then the big bombshell. Towards the end of the 90s, oscillations were discovered. This is the first and still the only definitive observation outside the standard model of particle physics. What does it mean? What are the consequences? Well, you've heard a lot today, and we're still trying to work it all out to find what it's done. There's a long way to go still. Particle physics groups which had stopped neutrino activities, like the Imperial one, realized that this decision needed reversing. And so early in this century, we formed, as Michelle just said, a new neutrino group to study oscillations under David Walk. This group slowly expanded, and in 2006, Morgan applied for a fixed-term lectureship to join the participation in the TTK experiment in Japan. I remember his CV very well. It was exceptional. Although then just a postdoc, he had masterminded the Cybrune experiment, which he described during the talk. This is a Fermilab, and had an active role in the other experiment at Fermilab at that time, Mini-Boon. He was appointed, quite naturally, and joined the team preparing for TTK. This is a big experiment, involving about 500 physicists from 12 countries. TTK would start data taking in 2010, and from then would dominate the world's long baseline neutrino experiments, as it continues to do so today. Within TTK, Morgan quickly made his mark, and in 2015, he was elected as co-spokesperson. TTK has two leaders, one Japanese and one international. Morgan was re-elected in 2017 to serve the maximum of 2 terms. Whilst co-leader of TTK, Morgan inspired the search for CP violation that we've heard about today in the neutrino area. It is one of the hottest topics in particle physics today. As you have heard, TTK now has evidence that this occurs. it has potentially profound consequences and for our understanding of the nature of the world, of the universe. At college, Morgan's position was made permanent, and he took over the leadership of the TTK group when David Walk left in 2013. He does many other things at college, and Michelle has already mentioned he now chairs the Juno Committee. So it's a valuable part. So it is a real pleasure that today we can celebrate his promotion to professor. And so, Morgan, many thanks again for this illuminating lecture. I regret a fully justified round of applause is not possible with this format, but for me, it has been a great pleasure to work with you and to offer you this vote of thanks. And I'm sure everyone listening wishes you further success in understanding these ghostly particles. Thank you so much.